Welcome to qnawire.
In this question, we are given a potential which is given as a constant multiplied by the absolute value of the distance or the position x. We want to find, first of all, what is the force, right? As a classical way of understanding this potential. Right, we know that force is equals to negative du dx. Now considering the case where x is positive, this will become dAx over dx, right? Negative of this value, which is just negative a. But in the case where x is negative, this will be negative d of negative ax times dx should give us positive a. And therefore, to accommodate these two results, right, we can just write f as being equals to negative a times absolute value of x over x. So what this actually helps us with is that if x is a positive value, right, this will be negative a. But if x is a negative value, this will be positive a. Right, you can see that this will divide each other because they have the same magnitude. You will get 1 or negative 1 based on the sign of our x. Now, this is of course not valid for x equals to 0, right? Just as how this potential, because it's not differentiable at x equals to 0, right? It's a kink at x equals to 0, this potential. Therefore, it's not differentiable at this particular point, and therefore the force is not actually valid at the kink, right, where x equals to 0. Now for the second part, we want to use the uncertainty principle. Similar to a previous question, right? We approximate the uncertainty principle to be h, right? This is definitely more than h bar over 2, right? So we can approximate this to be about h, getting rid of the numerical factors, right? And we're gonna assume or make an approximation that the uncertainty is also equals to the value of x, right? So xp is approximately h. With this, we can write down the energy of the particle, total energy, as a function of h, right? Because energy is just kinetic energy plus potential energy. It's p squared over 2m plus a times x. Now p squared, in this case, because px is h, so p will be approximately h over x. Now considering as only x being more than 0, right, if we consider x as a positive value, then our E will become h squared over 2mx squared plus ax. We can find the x value that will give a minimum, minimum energy, right? That is what we want because we want the 0 point energy, right? Just have to differentiate E with respect to X and we equate this to 0. So this is our expression. You can get x cubed to be equals to h squared over m times a. Right, and therefore x is equals to square over m times a power of root 3. With this value of x, we can find the minimum energy, right, the 0 point energy, substituting this back into our equation for energy when x is more than 0. To be equals to h squared over 2m times 2/3 to the power of 2/3 plus a times h squared over ma to the power of 1/3. And if we were to actually open up the brackets a bit, right, you will see that this is actually 4/3 h, right, h to the power of 4/3. So h squared minus away 4/3, right, so just 2 minus 4/3 is about 2/3 by 2. For the m, this is 2/3. This will be m to the power of 1/3, and then we have a to the power of 2/3. For the second term, we do the same thing, we open up the brackets. So a is 1 minus 1/3, get a to the power of 2/3. h will be 2/3, m is 1/3. And we see that they have the same common factors, right? So it's just half of these common factors plus one of these common factors. Therefore we end up for energy with 3/2 times these common factors, which are a square h square divided by m all to the power of 1/3. Right, so this is our 0 point energy. And if we were to consider the negative x part, it will give us the same energy because this is symmetric about 0. Right, so therefore the energy should be the same.